I think we can wait for 5 minutes, then we can start. So I think we can start now. So first we'll try to solve some of the MCQ-based questions, and then we'll move to the some numerical questions that we'll be solving. So, first question says that because this is mostly based on sintering and related phenomenon, so the lecture will be, or the questions will be basically focused on sintering. So, the first question says, during sintering, pores in the sintering materials are involved in, like during the sintering process, the pores are involved in what kind of reactions and transport. So first is mass transport, second is densification, third is grain coarsening, uh, fourth is gas reactions, and all of the above. So you have to tell which of the options is right for this question. So can you answer, like, what is the right answer for this? Basically, the sintering process is that after compacting the mold, we have the compacted mass of a material, and then we are trying to sinter it to post compaction, and there are certain pores present inside this compact. And for during the sintering process, what happens is that these pores, obviously because we are trying to decrease the porosity of the material, the pores will try to be annihilated, and then we have a higher density of the material. So for annihilation of these pores, there are chances that when there are different methods of filling of these pores. One of that is mass transport, where we have the pores that are created in the compact, and the material from some other portion will try to and occupy this pore or vacancy, and as a result the material will be densified. So we can say that during the sintering process, the mass transport occurs of the pores. That is right option, because that will help in achieving a higher density of the material. Obviously, because the pores are involved in densification process also. As you are decreasing the pores, you are increasing the density of the material. The grain coarsening is also a phenomenon associated with the pores, because as you go for a higher sintering temperature, the grain growth takes place, and as the grains grow, the pores that are present along the grain boundaries, they also try to break away from the grain boundary, and as a result, they have a role to play in during the grain coarsening reaction. The pores are separated from the grain boundaries. And also gas reactions, because if there are certain gaseous compounds in the material, through these pores there is a release of those gaseous atoms, such as hydrogen, for example, or CO2. These gas reactions are removed through these porosities, and as a result, during sintering, the pores are involved in all of these phenomena. So the right option is all of the above. Now next question says that the limit of densification in sintering can be marked from moving of pores, moving of grain boundary, attaching of pore or grain boundary, or separation of the pore grain boundary. So you just have to say, because there are certain phenomena occurring during the sintering process, and in sintering you will have a point where there will be no further densification. Like for example, if you are increasing the sintering temperature or time, there is a time where this densification is reached and you do not have any further change in the density. So you have reached a maximum densification. So this maximum densification is actually marked by one of the phenomena. So it is saying moving of the pores, moving of the grain boundary, the attaching of the pore or grain boundary, or separation of the pore or grain boundary. So the right answer is separation of pore and grain boundary. Actually, what happens when you are trying to sinter the material at a high temperature, in the material there's a tendency for the pores to exist along the grain boundaries. So this pore needs to be removed from this grain boundary, and as a result, once this pore is removed from the grain boundary, a maximum density will be achieved. So as you are increasing the sintering temperature, the grains tend to grow. There is grain coarsening happening, and because of the grain coarsening, and because the spore is not able to move at the same speed with which the grain is moving, grain grow or boundary is moving for that matter. So because of that, we'll have a separation of the pore and the grain boundary, and as a result, we'll achieve a maximum density in the material. So the separation of pore and grain boundary is the right option. Then now next question is that at high temperature of sintering, the pores break away from grain boundaries because pores migrate slowly, pores migrate rapidly, decrease of grain boundary motion, or lower grain growth. So you can answer this question if anybody of you can answer it. That what is the reason for breaking away of the pores at higher temperature from the grain boundary? Is it because the pores are migrating very slowly, or they are moving very rapidly, or it is because of the decreasing grain boundary motion or lower grain growth? Can anyone of you try to answer this? What do you think is the right answer? Anyone can answer that? Okay. Basically, what happens when you are having a high temp, as I said, that you have a grain and this is your grain, and if you have a pore just at the grain boundary, when you are increasing the temperature, what happens? There is a tendency for grains to grow, because there is a phenomenon called as grain growth. At high temperature, the grains tend to grow because they try to uh, the smaller grains which are present in the material, they try to get joined together and they form some bigger grains. So if there are, say for example, 4 grains at higher temperature, you will have, say for example, 2 grains, because all the smaller grains have been occupied in the higher grains. So there is a phenomenon that occurring that is called as a grain growth. So because of the grain growth, what happens? The grain boundaries tend to move with the growth of the grains, and as the grain boundary moves, the pores which are present along the grain boundary are not able to migrate as easily as with the grain boundary. So as a result, what happens? The pores are left behind while the grain is moving in some direction. As a result, the pores and the grain boundary break away. So there is a point where they break away from one another. And it is not because of the pores moving faster, it is because pores are migrating very slowly, while the grain boundary is moving faster at high temperature because of grain coarsening or grain growth. So pores migrate slowly is the right option. In this case, that will help in breaking away of the pores from the grain boundary. Okay. Now we have another question that says dash lowers the sintering temperature of a material. Is it chemical addition, external electric field, mixed phases? So you have a certain sintering temperature at which you tend to have a higher density of a material. You want to achieve a compact. So if you make some additions into the material, whether it is a chemical addition or it is an external electric field or it is a mixed phases, so which of the following will help in lowering the sintering temperature of the material? Can you lowering the sintering temperature of the material, which is right, because as you add these additives, the porosity of the material is being covered, and as a result, you will have a lower temperature. You can achieve a higher density of the material. Okay, so all of the three options are right. Now we have another question that says, during sintering, if the system energy is increased, pores can be found along the grain boundary at grain interior surface, both A and C. So it is actually when you are having a grain boundary, when you are having a say for example a grain boundary, and at the grain boundary there is a pore. What happens actually? Grain boundaries are the regions of high energy regions. They are classified as one of the form of defects. So they have very high energy regions in a crystal, in a grain, in a matrix or in a grain. So this grain boundary area, when it is occupied by the pores, the surface energy of the system is actually decreased, because you are trying to cover a region which is having a very high surface energy. So if you are having a pore along the grain boundary, then the surface energy of the system is actually or the system energy of the system is decreased. So you will have a lower energy. But if the pore is inside a grain, then you do not have, or you have a higher surface energy you need to have, because there is another surface that is being created inside the material. So you will have a system energy that is increased. So when you have a grain say pore inside the grain, then you have surface energy or the system energy which is high in comparison to a system where you have a pore at the edges or at the along the grain boundary. So the option B is right, where we are saying that at the grain interior the system energy will be increased if the pores are found inside the grain. So inside the grain the system energy will increase, at the grain boundary the system energy will decrease. Okay. Now we have another question that says, minimal dimensional change in die compaction method can be achieved with following. So if we have, for example, the method of because we are saying that the densification or the sintering parameters will be largely dependent on how uh, like how we have compacted the material, because that will help in reducing of your porosities. So if for example we are saying that the compaction is achieved during the compaction process, what happens, there are certain dimensional tolerances of the material. Say for example you want to make a material of this shape, but when you are trying to sinter it, or first you have compacted it, and after sintering your dimensionals will be decreases because of the shrinkage. And this shrinkage is mostly because your pores are being annihilated, your pores are being occupied by the material. So you will have a shrinkage in the material, and that shrinkage will give you a dimension which is less than what is required for a say for example from the compact, less than from what it was in the compact. But we want to reduce these dimensional changes. So how can they be achieved? There are different options. First is if you have uniform geometries, small compact heights, low sintering temperatures, high pressure, or of the above. So you have to say which of the following option is right for minimal dimensional changes. This is actually, yes. Okay, so is there any answer? Okay, all of the above. So yes, right answer is all of the above. Okay, so all of these options are actually decreasing the dimensions in a die. Now we have another question that says, mixed powder sintering is used to form the composites, alloys, compounds, or all of the following, because we are having a mixed powder sintering. That means we are having phase 1 and we are having phase 2. So if there are two phases, for example phase 1 and then we have phase 2, and if these two phases are being mixed together and sintered, so we have different uh, type of products that are formed. One of them is composites, One of it is alloys, because if you are mechanically alloying them and then you are sintering them, you can form alloys, or they can form compounds. So it is possible that if you are mixing the powders and then you are sintering them, you can have composites, alloys, compounds, and all of the above, and it will depend of it will actually depend on how you are what are the two materials. If for example one of the material which is B, if there are two grains, this is a grain A and this is grain B, and this is grain A for example, and this is grain A, and then you are inserting grain B inside the material, and this grain B is, say for example, a low temperature melting element, so it has low melting point. So during the sintering, this process will melt and it will try to occupy all the voids or pores inside the material, and as such you can have a liquid material that has been solidified during the sintering process, and it has covered all your pores or voids. So you can form a composite, you can form an alloy, or you can form a compound based on your sintering processes, based on your sintering temperature, based on your type of powders that you are using. So now we have one question that says that this is a question that is based on your shrinkage, because that will help you to understand how shrinkages work in a material. So the question says that you have a tungsten powder which is pressed at 150 MPa to a green density of 55%. Okay. After sintering, the compact attains 86.8% of its theoretical density. Okay, so you have to achieve a density which is near about the theoretical density. That is what is required from powder metallurgy, that you achieve the density of the material is as close to its theoretical density. So after sintering, you are able to achieve 86% of the theoretical density only, while after compaction, the green density, which is 55%. So assuming uniform shrinkage, that means that you are assuming that the material is shrinking at uniformly throughout. There is no isotropy in it. So for example, so there is no anisotropy in it. So for example, if the material is here, the shrinkages through this dimension or through this dimension are all same. And it is saying that the linear shrinkage is in percentage is what? You have to identify what is the linear shrinkage. So what of us will write down what are the parameters that we have been given. We have been given that there is a pressure that is being exerted on the compact, and that is equal to 150 MPa. Okay, and then we are saying that we have been given a green density of 55%. So this is green density, and we have been given a say for example a sinter density, the density after sintering, that is delta S, which we have the rho S we have shown here. So that is 86.8% actually. This is 86.8 of its theoretical density. So as per the formula that gives you a relationship between your green density, you need to have a relationship between green density, the density, center density, and with your shrinkage, because we are assuming it is a linear shrinkage. So you have a linear shrinkage like this, delta L by L, L naught, say for example. So you need to use the relationship between these three and find the linear shrinkage in percentage. You can take 5 minutes and try to answer, then I'll also solve it with you. So based on your relationship between the green density, sinter density and linear shrinkage, you have to calculate what is the percentage of linear shrinkage. So I'll write down the relationship first between the green density and sinter density. So you know that the sinter density, one second, This is your center density, that is equal to your green density. So this is your relationship. Okay. We have a relationship between sintered green and this. So we can write that the sinter density is obviously, because the sinter density will be higher than what will be the green density. So the sinter density is here given as, so we can write this whole thing like 55, because this is 55%. So we are assuming the theoretical density to be say 100%. In out of that 100%, 55 is the green density, and with respect to the theoretical density, the center density is 86.8. So this is 55 divided by 86.8 is equal to 1 minus del L by L cube. Okay, so now you can say what is 55 point divided by 86.8. 55 divided by 86.8, so this is 0.633 raised to power 1 by 3 is equal to 1 minus del L by L. Okay, so can you calculate now what is the value for this? So we can say it is 0.633. So I think we will have a value of del L by L equal to 0.14. So this is your the linear shrinkage, because this is the fraction. It is in terms of fraction. This is delta L by L, the change in the dimension L, in linear dimension L, and then with respect to the total dimension of L, it is equal to 14%. So you can say that we'll have a linear shrinkage of 14% based on this data. If you have a theoretical, you are given a compact and green density of the material. Is it clear? Is it clear? Okay. So now you have to also calculate the densification. So how will you calculate the densification? You know there is a relationship for densification that is given by this formula. That is your density of center minus your density of your green divided by the density that you theoretically want to achieve minus the green density. So this is your densification, because you're asked to calculate the densification. So you can take the theoretical density as 1 here, because we can take all of this in the form of fractions. So we can take theoretical density, say for example 1. So the center density will be 0.55, sorry, 0.865, 0.865 minus the density of your green compact, that is 0.55, divided by the theoretical density, that is 1, minus your green density, that is 0.55. So what is the densification? That is 0.7. Is it right? Okay. So now this is clear. So can we move to next question? I think we can go to the next question now. So now this question says that we have a tungsten nickel compact. So as we said that we can have two different mixed powders and then we can form a compact from it. We can form say for example a composite material out of it, or alloy, or compound out of it. So here we have a compounded material. We have two materials together, tungsten and another is nickel. So if you have a tungsten nickel compact, it is prepared by liquid phase sintering at 1500 degrees Celsius. So in liquid phase sintering, one of the metal will be actually melting along the grain boundaries and it will fill the spaces between the grains. Okay, so you are doing the sintering process at 1500 degrees Celsius. So it is saying that if the size of the tungsten grain is 40 microns and the interfacial tungsten and tungsten nickel energies are given like this, the predicted next size of sintered tungsten grain is what? So you have to calculate the predicted next size. Next size is actually x by d ratio. You know that. You have to calculate the x by d. So what you are actually given here, you are given that you have two grains. First off, say for example this is your tungsten grain and then this is also your tungsten grain. Okay, and because you are doing a liquid phase sintering, there is a this nickel that will be present inside in the form of a liquid sinter, right? So this is your nickel grain. So you are trying to sinter it with the help of liquid phase sintering. So you have three particles in contact now. If we will try to draw it clearly, so we can have something like this. So we have this, and then we have a nickel here. Okay, so this is tungsten, this is tungsten, this is your nickel particle. So this is what is being said. So this is your grain. So you can say this is a grain boundary. Okay. So we are given an interfacial tungsten. So what is interfacial tungsten? That is the surface energy between tungsten and tungsten atom. So that is given by 0.52. And then we have also given the interfacial energy between tungsten and nickel. So this is tungsten and nickel, that is given by 0.32. Okay, and you have to calculate the predicted neck. So what we are actually doing, you also know that there is this angle that is between these two. There is an angle that is formed and this angle is called as dihedral angle. So this is given by theta. So this angle that is formed between the two particles, when the third particle is just filling the space in between the two, this is called as a dihedral angle. So we have this angle which is called as a dihedral angle. Okay, now where are these interfacial energies actually acting? Between tungsten we have this interfacial energy, right? Between this nickel and tungsten we have the interfacial between tungsten to nickel, and here also it is tungsten and nickel. Okay, now based on this geometry you have to calculate the x by d ratio. So you can take 2 minutes to try to solve it, then I will show you how to do it. I have given all the parameters that are given. I have put them down. So you just have to find out the value. How is x by d will be calculated? You just have to use the geometry for that. Also, this x is actually your neck diameter. So this is the x is always taken. What is this interaction between the tungsten and tungsten? You have to actually assume this is not just a circle. This is a sphere. So this is a three-dimensional model. So in three-dimensional model, when you have an interaction between this atom and this atom, it will be joined at this position, and at this position you can assume it to be a form of a circle. There is this interaction between the two, which is in tungsten, which is tungsten, and this interaction between the two is in the form of a circle. So you can say it is of diameter x. Okay, the diameter of this circle which is interacting between the two molecules is given is actually x, you know that, and the whole diameter of this particle is actually d. That is how you are able to calculate this neck size. So you just have to use your equations. You just have to balance your surface energies. So for example, if you do one thing, you try to take this dihedral angle and you will have these two angles. This is now theta by 2. Okay, this is also theta by 2. So if you try to balance the surface energies, because this is some vertical component of the surface energy, these are some like at an angle some components of your energy. So you just have to balance your energies. So for example, we can say that the interaction of tungsten WW, this is the vertical component. It will be balanced by some vertical component that will be a function of these tungsten nickel surface energies. So we can do like this. We can say, because this is your theta, the vertical component will be cos of theta when you're trying to balance it, right? So you can say this is your surface energy between tungsten and nickel, and cos of theta, cos of actually theta by 2. This is your this energy. When you try to resolve your surface energy between tungsten and nickel, you will have a surface energy that is along the vertical direction, and that will be given by this, and it will be summed with your tungsten energy between your tungsten and nickel again, but cos of theta by 2. Is it clear? So we will have the surface energy between tungsten and tungsten equal to 2 times the surface energy between tungsten and nickel cos of theta by 2. Okay, so now you have this relationship. You can say that cos of theta by 2 is equal to the surface energy for your uh, tungsten between your interfacial energy between your tungsten atoms, and 2 times the surface energy between your tungsten and nickel. So this will be equal to, because the values are given, so this will be 0.52 divided by 2 times 0.32. So what is the value for this cos theta by 2? So it is 0.52 divided by 2 divided 0.32. So this is 0.81. So you can calculate cos of 0. You can calculate theta by 2. That is 35, I think. Can anybody calculate what is the value of theta? Theta by 2 actually. So we just have to calculate the value of theta by 2. anybody calculate the value of theta by 2? We just have to calculate theta by 2 here first. Okay, so this is 35.6. But you have to calculate this x by d. So how you will calculate x by d? Your x is this. Say for example, if you try to see, because I told you this is the diameter of your this circle. So this is the circle that is being formed at the interface of your tungsten, and it has some diameter x. But you know that the diameter from this interface to your center of your tungsten, that is d. This is also d. And there is an angle here between the center of this tungsten atom and the interface between the tungsten atom, and you can just draw a triangle like this here, and that angle between the two will be also theta by 2. So I can write it here. I can write that it is sine of theta by 2 is equal to x by 2 divided by, because this is perpendicular, this is your the uh, angle, and this is its perpendicular, and can write and the this distance between the two, so this will be d by 2. From here you can calculate x by d, right? So your sine theta by 2 x by d. So you can calculate the x by d from here. So sine of theta by 2, that is theta by 2 is 35.6. So you have sine of 35.6, that is 0.58. So you can calculate x as 0.58 into, because the diameter of your grain is given, the size of the tungsten grain is 40 micron. So you know the micron diameter, so that is 40. So your this neck diameter will be 0. No, I think it will be 23. So I think it will be 23.28. Okay. So this is your this width between the two particles. Like this is your neck diameter. Is it clear? Is there any question? Then we can move to the next question. If there is no question, then we can move to the next question. I think we can move to the next question now. So this is your another question. This is based on how your mechanism of diffusion occurs inside the material, and also it is relevant how your because your neck growth, your compaction process, your sintering process is all influenced by the mechanism of mass transport and like diffusion control. So this will help you to understand those kind of problems where you have diffusion based processes. So you have a question that says a steel specimen containing 0.2 weight% carbon is carburized in an atmosphere that maintains a carbon concentration of 1.2 weight percentage at the surface of the specimen. So actually you have a specimen like this. You already know the concentration inside of the material. This is a steel specimen, so the concentration, which is the initial concentration, is 0.2, and you're trying to carbonize it in an atmosphere, and that atmosphere is having a carbon percentage of 1.2. So this is your concentration gradient, and as there is a concentration gradient, there will always be a transfer of these carbon atoms from a high concentration gradient to a low concentration gradient, which is the diffusion process. So it will try to attain equilibrium and will try to carbonize the material. So you are given the two concentrations. One is the surface concentration and one is the actual concentration. And then you are given that for carbon diffusion in austenite, d naught, which is the diffusion coefficient, which is given to be 2 into 10 to the power minus 5. Okay, you are also given the activation energy value, and now you have to calculate what is the depth from the surface of the specimen at which a composition of 0.4 weight percentage is obtained after carbonizing at 8 times. So you are carbonizing at certain conditions, and obviously because there is a gradient, there will be a there will be different concentrations of inside the material. Say 1.2, there will be 1.1 carbon, there will be 1.0 carbon, and then you have to see at what point you are having a concentration of 0.4. As you are moving in the direction, as you are moving in the depth of the material, there will be a difference in the concentration gradient, and you just have to calculate where exactly will be this 0.4 percentage of carbon present inside the material. See, so now you know I'll write a general formula, then you can first try to solve it. So you know the concentration gradient is given by this formula, which is dependent on your how much distance it has covered and in how much time, because concentration or diffusion is time dependent. It is temperature dependent also, but because we are given certain temperature. So it is concentration gradient or the diffusion process is largely dependent on your temperature, time, on the depth of the material. Okay, so this is given to be A minus B into ERF, which is a function. This is a function, and it is having a value of x by and 2 times under root of dt. So this is your diffusion coefficient, this is your temperature, and this is the depth at which you're talking about x, and these are some constants. So this is your general formula for a concentration, right? At actually when you are trying to start the when you are initially starting this carbonization process or diffusion process, this A is equal to Cs, that is the concentration at the surface, and this D is actually given by Cs, concentration at the surface, minus what is the concentration at the bulk of the material, which is here 0.2. Okay, and you are also given one of the formula, which is the based on your diffusion coefficient, that is D is equal to D naught e raised to power minus q. Q is the activation energy divided by R times T. T is the temperature. Okay. So actually, if you use this formula, the values that you have this D naught that is given in the question. You have this activation energy that is also given. You know R, that is 8.314, 8.314 in kilojoules per mole. Okay, and then you know this temperature also within Kelvin, you have to convert it. 870 plus 270 3 Kelvin. Okay, so you can calculate this value of D. So first we'll calculate this value of D, then we'll put it in this, and then only we can be able to calculate this X. Because in order to utilize this equation, we need to know first there is a function, we'll do that. We need to know the value of D, we need to know value of time. Time we know that it is carried out for 10 hours. We know the concentration at the surface. We know concentration at the surface and concentration at the bulk. So, and what is the concentration that we want to achieve? We want to achieve 0.4. So all other parameters are given, all in order to find this X. So for that, we just need to find this D first. That is the diffusion coefficient in terms of the activation energy. So first you try to solve this diffusion coefficient value. So how will you do that? We will put the value of D naught, that is given by 2 into 10 to the power of minus 5 e to the power of activation energy, that is given by 142 kilojoules per mole. Okay, so we can write it as e raised to power minus q is 142 into 10 to the power minus 3, because it is in kilojoules, we'll convert it into joules. And then we have value of R, that is 8.314, and then we are given temperature. So 870 is the Celsius, so it will be 870 plus 273, so that will be 1143. 1143 is your temperature. So you just have to solve this equation to find D. We can calculate it and write down the answer. I think the answer is 6.4247, I think. 6.47 into 10 to the power minus 12 meter square per second. So this is the value of your D. Okay, is it clear? Is everybody got the same answer? So now you have got the answer. Now first, just to have one more slide. So just to have space, 1 second, we'll just do one thing. Okay, so now you know value of D. Okay, so now what we have, we have the value of your this in this equation we have the value of D, we know the value of time, we just have to calculate X, and we know the value of C at a constant, at a depth of X at a time T, so that is 0.4 for us. So how will we do that? We will write down 0.4 is your concentration that you want to achieve at a surface concentration of say for example 1.2, because that is how what we are started with, plus we need to see there we have Cs minus C naught, that is surface concentration, 1.2 minus what was the bulk concentration, that was 0.2, into ERF of X, that is what we have to find, divided by 2 under root of D into T. So you know the value of D and T, you just have to put the value of D and T here. So first we'll try to solve this. So this will be 0 point, I think 8. You will have something like this. 0 0.8 is equal to ERF x by 2 under root of dt. So you have been given that if you do a ERF function of certain value, say you treat whole of this as y. Okay, so you can say is equal to ERF y. So now the ERF y will be somewhere here between 0.79 and 0.82. Somewhere here you can have a value of 0.8, right? So you just have to calculate from this table what should be the value of y in order to have a value of 0.8 as ERF y. So the right hand side of the equation is ERF y, the left hand side of the equation shows 0.8. So you will give 0.8 here, and based on the interpolation method you can calculate at what value will you be able to get your value of, say for example, ERF y. You can do it based on first and third also. You can do based on your second and third value. So say for example, I'll try to do it with first and last. So I'll do like this interpolation. I'll try to take these values, this and this and this, and this is also given. So how will I try to do? I'll try to say that for here I will have some value, say for example some z. So I have to calculate what is the value of the z when the ERF value is 0.8. So that will be the z minus 0.85 by interpolation method divided by, if it is 0.95 minus this z value, that will give me 0.8 minus 0.7707 divided by 0.8209 minus 0.8. Okay, so you can calculate based on this the value of your z, right? Or you can do one thing, because there will be 2 times and it will be squared. So you can do one thing, you can do this 0.95 in order to have only one z, because we want to have a linear equation. 0.95 minus 0.85, and here we will write 0.7707. Okay, so first I'll try to solve what is on the right hand side. So that is 0.8 minus 0.7707 divided by 0.8209 minus 0.7707. So this will be something as 0.58. Okay, 0.58. So I can calculate z as equal to 0.58 minus, I think it is something like 0.908. You might get a slightly different value if you choose different starting and end points, because you're just interpolating the data. You are just trying to see where this data point will come, because this is just a curve. For example, if you have a curve and you have certain y value and you have a ERF value, so if you just know this data point and this data point, and you're just trying to see what is this data point in the middle. So it can vary slightly. So you can have a z value is 0.908 something that is coming. So I can put it in this equation now. Here it was ERF y 0.8. Now I know that this y is equal to 0.908. So I can write that x divided by 2 under root of dt is equal to 0.908. Okay, now you can tell me the value of x, because you know the value of d, you have calculated it, you know the value of time. So based on this, you can, because this is in seconds, you also have to calculate this time in seconds. So this is 10 into 60, that will give you minutes, into 16, that will give you seconds. So you have to use the value of time. So can you tell me what is the value of x? It will be slightly different for each of you, but you can try to calculate the value of x. Has anybody calculated the answer? It is around 8.65. Yes, 0.87 mm. It can also be like that. So we can convert it, and there is a possibility of certain variations because of the way we have interpolated it. So we can have a variation. So I can also convert it to in microns. So this will be 865 micrometer. So this is the depth. That means that at a depth of, because the surface is carbonized, so only at a depth of your 865 micrometer you will have a concentration of 0.4 or percentage of carbon. So this is your answer. So is it clear? Is there any more questions from your side? Any doubt or any question? If there is no question for today, then I think that is all for today. So if you have any question, please you can ask that. So I think that is all for today. So thank you. I'll end it the class today. Okay, you have a question that says that dislocation density. Actually, yes, because when you have a, say for example, if you have a material, any material will have certain defects in it. So those certain defects are referred to as, there are different types of defects. There are line defects, there are surface defects, and one of the defect is the dislocation. So what you actually have, you have different, for example, in a material. So if you have a material, you have a grain like this, and there are dislocations present in the material. So these dislocations have a very important role to play in for a material. One of the important role is that they have a work hardening effect. What is work hardening? That this will tend to have a high strength materials, because these dislocations will prevent the grains to grow, will prevent the any deformations to occur in the material. So you need to know that deformation and your dislocations, they are directly related. If you have a very high dislocation density inside the material, that means then there are large number of defects inside the material, and then you can deform the material and you can have a higher strength in the material. So higher dislocations means higher strength in the material, because you will be able to work hard in it, because these dislocations will try to have a pinning effect inside the material, and that pinning effect will prevent your grain growth, it will prevent your deformation, it will prevent your fracturing to occur. So this dislocation is favorable for a higher work hardening effect. In terms of powder metallurgy, they are important because when you are trying to compact a material, there are two things that can happen. One thing is that it can fragment, or it can break down, because the particles are under compression, they are under extreme stress, and because the material does not have enough strength to be compacted, it will fragment. So the particles will try to fragment themselves. And there is one more other thing, that is there will be plastic deformation, and whenever there is a plastic deformation, the material will try to deform itself, and it will try to gather the energy whatever you are providing it, and it will try to store that energy, so that will be accumulated in the form of strength of the material. So if you have a stress strain curve and you will achieve a plastic deformation for a material, you will be having a higher strength for a material. So say for example, for this metallic material, the high plastic deformation is possible because you have a high dislocations present them, high dislocation densities, and the fragmentation is not occurring there, because once the fragmentation occurs, you are just breaking the particles into into pieces, and then you not have a desired strength. So this dislocation or dislocation density is nothing, it is just how many dislocations are present per unit area of the say for example of the sample, or per unit volume of the sample. So if you have high dislocation density, you are able to deform a material to a larger extent. You will be having a higher plastic deformation. This higher plastic deformation is favorable for powder metallurgy, because if it is deforming plastically, then you can have this annihilation of the whites. There will be a loss in the porosity in the material. So you will have a higher strength in the material. You will have higher density of the material. So this dislocation is important when you're talking about say metallic materials. So they always have a dislocation present in them, and that will help them to achieve higher strength. Anything else? Uh, Vacancy density. I don't know what you mean by vacancy density. But vacancy is a defect which is a three-dimensional defect, while as dislocation is not a three-dimensional defect. So if you mean to say like that, I don't know what you mean by vacancy density. So yes, both of them are defects. Yes, vacancy concentration is different from, yes, vacancy concentration is different from, because vacancy is a three-dimensional defect, while its dislocation is a linear defect. Okay, so I think that is all for today. So thank you.